Hello, so this is the second part of my review of lecture 23, differential equation and exponential of a. So after we discussed the first part, which is the main formula that we learned for this lesson, du over dt equals au, and we have the general solution for that. And now let's talk about the second one, which is the stability. And let me review quickly about the last answer that we have from doing the example. The ut, we said st goes to infinity, it will converge to this only this first term right here, because here the t will goes to 0, right? In this part the second term will goes to 0. Okay, so this is, I call this one the steady state. So it will be steady as t equals go to infinity. There's another term which is called the stables, which is as t goes to infinity, does the solution of ut approach 0? So there's a subtle difference here between the steady state and the stable. So the stable is defined when our solution goes to the 0, but the steady state goes to some constant here. Okay, so I just want to keep that in mind. And this part right here will discuss about the stability. So what defines our steady state in this case? What defines that this term goes to 0? What makes this term goes to 0? Of course, it's this one right here, the eigenvalues, the lambda, because the lambda is -3, because this term will goes to 0 as t goes higher and higher, right? While in this case the lambda is 0, so the solution as t goes to infinity is the steady state. So the lambda has played a significant role there to kind of determine whether our solution ut will be stable or will blow up. So that's also another term, blow up. So imagine that if I have the lambda that is positive number +3 in this case, then the system will blow up, right? Because as t goes to infinity, this term will be like also goes to infinity, and our system will blow up. Let me just have that term, the blow up. Okay, so let's discuss the possibility of the lambda, the eigenvalues, given all these conditions. Okay, let me delete this one. Okay, so we have these three conditions, so let's discuss them one by one. First, we have the stable, which is defined as the solution goes to 0 as the time goes to infinity. So let's see, when does that happen? Of course, all the solution goes to 0. Imagine that we have like u equal to some e to the lambda t x1, e to the lambda 2 x2, and so on. Of course, this will all goes to 0 if all those lambdas are smaller than 0, right? Meaning if it is negative. So let's write that down. So given so if this will be stable if all the lambda is negative. Okay, and then let's discuss briefly about the condition where we have the complex eigenvalue. So remember, it will be in this form, a plus b I. The complex, we have this complex term right here. So in this case, then how do we define whether it will be blow up, stable, or anything? How do we value this? Does this negative? Does this positive? So what matters here is only the real part, because if we plug it into this term right here, so let's say I, let's give a real number. Let's see, like 2 plus 3i, and then actually what matters is the absolute value of the e, right? So it is st, because lambda t, and then if we divide them, then we have this, and then we have this, and this term right here, the absolute value of whatever it is, of t is actually equal to the cos square and the sin square, and this will be 0. Okay, so this is actually defined in the Euler's form. So in Euler's form you have like this equal to the cos theta plus the sine of theta. And when you want to find the absolute value, let's say you have a complex number here of a and b, and you have to you want to find the absolute value, then all you have to do is just like the Pythagoras theorem, so you ignore the I and then you square a and b square and then you root them. So you want to find this absolute value of this, but this one is cos theta plus sine theta, so you ignore the I and then you left with this square of theta and sine square of theta, so you left with 1. So this is 1. So all that matters is this term right here, so this one. Okay, well, you may be wondering why we suddenly interested in this absolute value of this, because we cannot define whether this will be negative or positive, right? Because there's this imaginary number and we need to transform this imaginary number, this complex term, to something that is real. So that's why we are interested in the absolute value of this term right here. So again, what matters is only the real part of this one, so I'm gonna write that down here too. So if all the real part, the RE, real part of the lambda is negative, okay? Write down all there. So if all the lambdas, the real part of the lambdas of our eigenvalues is negative, then our system is stable. Let me delete all of that for a while. Now, how about the second one, the steady state one? Exactly as what we had earlier, so we know that one of them, or at least some of them, must be 0, and then the rest of them and the other we will have the same, okay? Because we need them to reach 0 as t goes to infinity, so we need them to be negative as well. Cool. And the third is actually the simplest one. It will blow up if any of the real part of our lovely lambda eigenvalues is positive. So remember this one, that those will define the stability, okay? And actually, if we have a matrix, let's take an example of 2 by 2 matrix. And we can tell by the trace or determinant how this matrix will behave. Will this be stable, blow up, or will this reach a steady state? So remember that the trace is the sum of the eigenvalues. So the trace has to be, of course, negative, right? Because by meaning that if we state that the lambda 1 plus lambda 2, so this is be negative, so this will be of course negative as well. Okay, so that's the first one. And how about the determinant? Because even with having this trace, negative trace is not enough. For example, this matrix, you see this trace sums up to negative, but then it will still blow up because there's this eigenvalue of 2, you see, because we will do here, like write this. Actually, I mean this one. This will be negative and this will be positive, so this will blow up. So you see, so this will be then lambda 1 will be minus 2, so this will be okay. This satisfy everything, but this one is positive. But the trace of them, the sum of trace, minus 2 plus 1 is still minus 1, negative. So this alone is not enough. So we need our second condition. We also need to make sure the determinant is satisfied, and the determinant needs to be positive. Why? Because we assume that all the eigenvalues is negative and negative times a negative number will be positive. So those are the two terms that governs whether our matrix will behave stable, steady state, or it will blow up. And these are all its conditions, and remember, only the real part of lambda of our eigenvalues that matters. Thank you.